actual data. Okay, so first order, raise your hand if you got first order. That only means that your data was good enough to get first order. It doesn't mean anything about you, okay? Good people. It's just that it's a little hard to get the crystal violet in the colorimeter super fast. What am I talking about right now? Giving you pieces of information for air analysis. Thank you. Okay, so it's hard to get the crystal violet in really fast with the sodium hydroxide. Some of you guys diluted it by putting a lot of sodium hydroxide in it, by like flooding it with sodium hydroxide. Some of you guys use different ratios, so that very well could have impacted your ability to get clean data. So we had one colorimeter that was on the Fritz, right? Binky's group. It was recording like 0.08, like super, super low observances, where some of those were like what? You guys, some of you guys had like one, close to one observance? No? Was that your highest? But y'all's ran for like 300 seconds. Yeah. But theirs only ran for like 20 seconds. So it very well could impact your linearity, right? Because towards the end of the graph, if you took data points too close to the end, it was already nearing zero very quickly. So that data may not be valid to put into your linear regression for your integrated rate laws. So your K values are where on your linear regression line. They're the slopes, so you can compare. You'll do percent error for each of these, okay? You can't do percent error, sorry. You can't do percent error for first or second order or zero. That's just weird, right? No percent error there. You can do percent error for your rate law constant. This is a relatively high or low rate law constant? High or low? Low, okay, so what does that tell you about the rate of this reaction? Kind of slow, right? So that's going to be allowing us to actually collect data so that it's not running so fast we can't collect data. So that's actually nice that it runs a little slow because our data should at least be attainable. Rate law, half-life, we got a close half-life.
We got like 10.1.
10.1, okay, so I did see like 190 something. So you guys can do your percent error there as well. So hopefully I had you have your laptops out so you could type this in right now, and you're making some notes so that you know where you're doing your percent error. And then I'm going to give you guys about, I don't know, 2 minutes in your lab groups. You need to sit together for a minute, 2 minutes. You need to decide, about your emails last night, decide on your real life kinetics idea that you want to focus on, and you guys can come right on the board because there will be nobody with the same idea. Okay, so kinetics of blank. If you're ready, come right on the board. And then we're going to...
Wait, on this one?
On this board, yeah.
Okay.
You got pharmaceutical, environmental, biological, that's not a reaction. Nope. It has to be a reaction, people. We're talking about reaction.
Haber process.
What's that?
Oh. Haber process?
Oh, Haber process?
Go listen, I want to
I don't care.
weather systems or free drying?
Go for it.
Weather systems free drying are the internal combustion loops.
So there's well, that is so you need to write down that order though.
Oh, you want to do?
So there's some schools in the usually it's yeah, for the relevance. All right, you have 1 more minute to make a decision, or I'm going to give you a really boring idea.
Freeze drying weather systems are the internal combustion engines.
I had one person do drugs last year. How about Tylenol?
Tylenol. You're right.
Talking about pharmaceuticals. That's all my classes.
No, it's I would. Let me actually show you. Let's do drugs. Let's do drugs. That's what I want to do. I want to be a pharmacist. Let's do drugs. I want to be a pharmacist. Like any research.
I do like if they get
I'm excited now. But not crystal math, not like that. We're talking about like ibuprofen. Yeah, the light stuff.
So yeah, I don't know any examples that we've gone over about making polymers.
The light stuff. Not like the hardcore like. We did drugs.
You need to specify. Because there's like
pharmaceutical.
everything's a pharmaceutical drug. Specify.
Um.
You'll specify it later. You probably need to research. Polymer science. There, that gives you a really broad area. You can narrow. Okay. Jacob's group, drugs is really broad. You're gonna narrow. Courtney's group, popcorn. I'm gonna say question marks. I need to make sure that's valid. It's more physical than chemical. I got one more group. Where are we at?
Environmental.
And thank you. Environmental. Choose something environmentally related. That gives you some leeway there. Okay.
What?
I have a question.
Yes.
Would painkillers be like specific?
Painkiller. That's still broad. I would do Tylenol, ibuprofen.
Oh, like specific,
Naproxen sodium,
okay,
like, because you
okay.
need to know the reaction.
Okay, pick,
Yeah.
I'm saying pick, I see what you're saying. I thought you were saying like pick like a field, like if we.
That's narrowing. Like
Yeah.
you're in drugs, now you're in painkillers, then you can go down further.
Gotcha.
Okay. Courtney, do you have something I do too?
I'm looking at it.
All right, so I've got a good start. Notes down. Laptop's halfway closed, so you're not so distracted. Or if you're in the middle of something, finish that real quickly. I'll tell you what we're doing next year, okay? I just want to wrap that up because when is your poster due? Friday. And it's a legit poster, right? If you need some library paper, I'll use your library paper. I've got some nice colorful papers down here. But you'll do like a 2-minute presentation on your topic, right? And at the very bottom of your Google Doc, I posted the instructions. Basically, you're going over, here's an important process you should know about. Here's the rate law for it. Here's the reaction for it. Here's why it's important in real life. And then I'll put it in the hallway so everybody can be informed about kinetics, right? Everybody needs to know about kinetics. All right, so laptop's halfway closed. We're moving to, I'm going to finish up the mechanism notes with you. I had like one more slide to do with you. Then we're doing Arrhenius, which in terms of Arrhenius's information, you got a good background from it last night. But the only other thing is we have to calculate. We're going to do some like 2 or 3 free response questions today. Okay, this is the piece of information I did not finish about mechanisms yesterday. Write down what you need to. Write down what you need to. I'll go over them as well. So we are nearing the end of kinetics. We're just trying to start trying to get our vocabulary right, because whenever you write your free response questions out for this one, you know how in thermochem where one word very well could have gotten you the point on the free response. That's kind of the same thing here. So when you're talking about intermediates on a graph, on like a multi-step reaction, how does the multi-step reaction look on a graph? First of all, pump, 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 right? It's got like 2, 3, or 4 little steps depending on how many elementary steps there are. Where's the intermediate there?
In between them.
Right, so if you have a 3-step reaction, the intermediates are here and here. 2 intermediates, right? Or depending on how many products to form, it could be more, but at least 2 intermediates. Where's the transition state? The peak, right? So this is intermediate. The activated complex, aka transition state, are at the top there. Are those are not as attainable. Those are not as likely to be able to isolate in the lab. Intermediates, for sure. You have that one step, it forms a product, you can actually capture that. You can collect it, you can put it in a little jar and keep it on your shelf, right? But a transition state, not so much, because a transition state exists as a really unstable kind of peak where the reactants are slowly morphing into products and the bonds are breaking and the bonds are forming at the same time. You can't capture that. So those are why those are 2 totally different things, and you should know the definitions of those. A catocarbon or carbocation is just an example of an intermediate. In terms of, this is what we went over yesterday, but we did say that the rate determining step is the slowest step, so it takes the longest to get to the peak, so the activation energy is the highest. We did actually talk about that. This is why we have those criteria of saying that a mechanism is viable. What were the criteria that we said that you have to verify a mechanism with? Think. Jack, tell me one.
That the coefficients have to match up with the rate law.
So I'm going to use the right word, molecularity. Okay, molecularity of, I'm going to say rate determining step must match the rate law. And there was one more, or there's 2 more, but one more, yeah. So I'm going to adjust that and say the sum of the elementary steps match the full reaction. And what you're saying is the coefficients match the full reaction. So I'm just going to say sum equals the whole. And then the other part is what?
It experimentally agrees with the rate law.
Right, so everything is experimentally determined, and so the rate law, which is experimentally found, agrees with the experimental mechanism. So those are really the two. The third one is like everything's elementary. It's experimentally determined. Catalysts, we went over briefly yesterday. We know that they are not consumed. They're found with both the beginning and the end, like in the elementary step. But there is sometimes, other reactions that could happen in our subset of our system. So that's where we can actually have them consumed by unwanted side reactions, meaning that they're not there anymore, or they're tainted, they're not complete. So, for example, in a biological system, AJ biology, right? What could happen to a catalyst in the body? As an enzyme, yeah. Right, a lot of acid, a lot of base, a lot of heat, and even sometimes cold. They denature them. Who remembers that from biology? Oh, so long ago, denature. Okay, so basically the enzyme's no longer usable because it's destroyed, but it's still there, but it's destroyed, right? Not useful. And then lastly, we have mentioned this twice now, but kinetics is, I want to know what's happening in between. Thermochem's like, I don't care about stuff in between, I want to know what's happening in the beginning and the end. So this one is path dependent, whereas thermochem is path independent. But we will talk about how they can influence each other, except for the catalysis part. So catalysts do not influence the delta H or the delta E. They only influence the activation energy EA, right? So they only influence EA. That's it. And the path taken, but that's kind of how EA comes into play. Right, so let's wrap up from yesterday. And then now Arrhenius. You ready? Maybe. I think my husband's getting me a cold, so stay away. Or maybe it's lack of sleep, or traveling, or dogs, I don't know. So many, I'm not running a controlled experiment to figure this out. I'll figure it out one day. Okay. So, maybe. Well, it probably helps if I actually plug the thing in. Yep. Teach chemistry. Okay. Yeah, it's still not going to work. So, Arrhenius. I'll do this question in a second with you. Oh, that was the concept map at the end. I just think it's good to study from. Do check that out. Okay, so this is just the reminders they told you. Remember at the beginning of the reading, it was like, here's what we know, here's what we know we can do. So talking about how, we know temperature does influence the rate, but it's not a linear relationship, and there has to be a reason for that. Second, we know that if you increase the temperature, the particles move faster, meaning when they move faster, they collide more frequently, and they actually collide with more energy. So those are the things we know, and hopefully they collide with enough energy to meet activation energy, hence the reaction would occur. So those are some of the things that you read about. The thing that worries us is that normally we want predictability, right? We're like, hey, increasing temperature, if I double the temperature, I should double the reaction rate. We think that's a linear relationship. We think that cause and effect is there, but it's not always true. So what's the other component of collisions that has to be perfect, not just the energy? Orientation, right? So orientation has to be right. So maybe there's a factor we have to consider with the orientation, which we've done no math with orientation, correct? No math, but that's where this math is coming in. So Arrhenius' equation is going to include a factor that includes how does orientation play into the reaction rate, and how does temperature play, like actual temperature calculations now, play into the reaction rate. We haven't done that yet. We've only compared rate and concentration, which is what kind of law? Rate and concentration. Those two data points give us the differential rate law, right? So rate versus concentration gives us differential rate law, which is just the generic rate law. Concentration and time gives us what? Integrated rate law. Now we're going to look at how does rate and temperature compare. So rate, in this case, it will be expressed as K as the rate law constant, but rate and temperature is going to be Arrhenius' equation. And that's it. That's it for rate laws, okay? So in terms of why does this not work, probably because the orientation's not right. Another thing to consider is, do you guys remember this from gases? Do you remember Boltzmann's curve? So Boltzmann's curve has that energy associated with the temperature. So if you don't know like for example, I could say the activation energy of a reaction is 100 kilojoules. So let's call this 100 kilojoules right here. And which line, the blue, the pink, or the red, has a larger portion of its particles meeting activation energy? Red, right? Looking at the area under the curve, you see there's a lot more red as compared to the teeny bit of blue here, and then the little bit more pink. You could actually figure out the area under the curve, right? Using math or something. Okay, so basically, that relationship though relates to temperature. So which is the hottest curve? The red one, right? So it's maybe at 1,000 Kelvin versus these other ones which are colder. And that relates to speed and so forth. I'm going to skip this part because you guys know how to break bonds. You guys know how to break bonds. Okay, so activation energy now is going to come into play with Arrhenius' equation. They call it the threshold energy, so if you hear that term, it's the same thing. You did read about that though. Do you remember that term? Yes? Okay. So if we're talking about reactants colliding, we hope that their bonds break. Because if they break, they can rearrange to form products. But if they don't break, they're just going to go up the curve. They're going to meet the activate complex, and then they'll roll right back down, and it looks like nothing happened because nothing did happen because the reactants didn't have enough energy to do their job. So we have to make sure they have enough activation energy. So once activation is considered, the observation is made that the reaction rate increases, but not to the full extent we think it does, right? So that's what I was saying earlier. If the energy part's met, great. That doesn't necessarily mean the orientation part is met. So that's why the molecular orientation has to be considered as well. So that's what's coming together now with the Arrhenius equation. Do you remember seeing this in your reading? This crazy, crazy equation. So what Arrhenius said was there's a threshold energy considered and the molecular orientations. So the molecular orientation is described as this P right here. And then it also relates to like how frequently do they actually meet with each other, which is the frequency. But I know I got time to calculate that. You're calculating something much simpler. But it comes all together with collision energy, orientation, frequency of collision, the rate of the reaction itself, the fraction that of particles that actually do have enough energy, activation energy, and the gas constant. What is this R value, by the way? We're talking about the gas constant, and we're talking about energy. Say again? 8.314 joules per. Okay. So now we're dealing with Kelvin again, right? So Kelvin is with us. Joules is with us again too. Okay. So here's what we're actually going to do. We're going to take that equation that's a little bit more complex and pull it into a linear regression, right? We're not going to take the calculus of it right now, but you can actually take the natural log of both of these sides, right? If you take the natural log of k, you get ln of k, right? Take the natural log of e to the negative activation energy divided by RT. How does that work when you take the natural log? Okay, so, well, you can also separate, right? Because they're added to each other. LN's added to each other. LN's multiplied by each other, become added. You know what I'm talking about? I like to pretend we can talk our mouth out. Okay, so ln of A, e to the negative RT. Oops. Negative EA over RT. You take the ln of that distributes to both those functions, I guess. So ln of A plus ln of E to the negative EA RT. This stays with us. What happens to this? It cancels. So that's where you're trying to pull the exponent down. So that cancels. Then you get negative EART, which we then separate into two kind of separate functions to make it look like y equals mx plus b. Do you see the y equals mx plus b? Okay, so what's the y-axis? ln of k, which is related to our rate itself. So we're not putting rate itself in there, we're putting the rate constant in there. But they're directly related because that's how our rate laws are related. What is this? Which is slope, okay. What is this? And what does the temperature have to be in? Kelvin, please do not put Celsius in there. And then this is going to be our y-intercept. But this is that A, which is the frequency factor. We will never actually calculate it. We're just going to say it's the y-intercept, or the ln of it is the y-intercept. We'll never calculate it ourselves. But it's the factor that includes like the frequency of collision, the ones that collide with enough energy, and the ones that collide with the correct orientation. It includes all those other constants together. but we won't really mess with it too much. So we're going to put this, just like we did with our other integrated rate laws, we'll put them in our L1 and L2 list, calculators. We're going to talk about how this looks data-wise, and then math-wise, and then what the heck does this mean-wise, okay? So you guys told me the linear regression kind of format. You also told me what the y and the x was. So what would you have to put in your calculator to calculate the slope? What would you be putting in L1? Whatever temperature, right? So you're doing a sketchy graph for yourself, because it'll help you your math, your equations, and your graphs kind of all come together. There's a lot of graphs in this unit. So what's going on the x-axis again? 1 over temperature. Oops. 1 over temperature. And that's in Kelvin. What's going on the y-axis? L and K. Okay, so what kind of data do you think is going to be given to you in the table? K and T. I won't give you rate laws. I won't give you rate. I'll give you the K value, the rate constant, and I'll give you temperature. Do you think I'm going to get 10 Kelvin? Maybe if I'm feeling good that day. Probably not. Probably Celsius. Okay. All right. So here's what your graph should resemble. So you'll have, and as you saw from the equation earlier, we have a negative slope. And what does the negative slope equal? What constants? Equals
divided by
okay, so m is equal to, it's equal to the negative, right? Because I did have a negative in the front. Negative EA over R. Okay, so my question here is, okay guys, you have the rates, constants, you have the temperatures. What is the activation energy? How would you find the activation energy?
negative R times the slope.
Negative R times the slope. So hold the R over, right? So multiply by negative R, multiply by negative R. Activation energy is then achieved. So you can figure out the activation energy not from a graph like the little coordinates, but from a graph like this. You guys ready to try? Yeah, okay. Oh, I had 2 more questions for you on this one, sorry. So this is for a reaction, right? For a single reaction, how many activation energies does it have? 1. So that's why you only have 1 activation energy. The slope is constant, right? It's a linear slope. The slope is constant. The activation energy is constant at every different temperature we can put it at. If I change the temperature, does it change the activation energy? What does it change? How fast? Jack, you're like, we're on the same wavelength, man. Okay, so it does not change the activation energy. It only changes how fast things go. Well, how are we expressing how fast things go in our stuff up here? Which of these relates to fastness? The K value, right, which is the rate law constant. So that's what it changes, right, because it changes as you increase temperature. And the ln of a K makes it smaller, right? Math relationship, so it's the inverse, but that's why it looks like it's getting smaller, but it's actually getting bigger. All right, so that's what that second question was. And then, yeah, we're good here, okay. So math, here we go. Here's your data. Let's put data in, and then we'll actually talk about the question. So it gives us a reaction. You want to put in your L1 and L2? Did you guys read the math help on the Arrhenius?
Yes.
It's like, put all the temperatures, put all the K values in, and then you to the tippy top. I love how she says that in the readings. Go to the tippy top of your L1 and L2, and then just do the function itself. All right, put this in my calculator. So Mr. Davis is taking some out. Yes, makes sense. So you're converting your temperatures to Kelvin, and you can do that in your L1. So 288. What is that? I knew that. Sorry, guys. 288, 298, 308, and then 318. Is that right? Okay. So you have your temperatures, and now you're not putting straight temperature in, you're putting 1 over temperature in there. You're not doing just straight K, you're putting, say again, Sean? ln of K. And then you're going to calculate. Am I moving too fast? You okay? Thanks, Alvin. Anybody other than Alvin okay? Thank you. Okay, so once you put your data in L1, L2, you go to your calc, you go to linreg. Alvin, did you do it? Okay, I'll come back to you. Can somebody raise their hand if they have it so I can get there? Go ahead, Vinky.
I got.
Tell me your linear regression line.
Negative 5,638.
Point something.
Yeah, 0.34.
Okay.
Plus 16.623.
Okay. Give me a thumbs up if you got that. Or hopefully something close unless you have something in there incorrect. Okay. So negative 5,638. What is that? I know that's your slope. Please don't say slope. What is that? That's activation energy over R, right? So M is equal to negative EA over R, and that's equal to negative 5,638.4. So how would I get EA? How would I get activation energy? Multiply by R. So I'm actually going to scratch R out. What's the value for R again? 8.134 joules per mole K. Love that you have your units there, Kurt. Thank you. So how do I get EA? This is X, right? So we're solving for EA. Great. Multiply both sides by, I'm going to go ahead and put the negative in there too. So the negative 8.31. So when you multiply by negative 8.31 on both sides, tell me what you get.
46877.15.
46877.15. So 46,000-ish, 49,000. Okay. What are the units? So say it again. Well, I'm going to stick with what it is right now. So what is it right now? It's joules per mole, because where's the K going? It's canceling out because the slope has temperature as a component of it, right? Because it's with X, so it does cancel the K out, the Kelvin out, so then it says joules per mole K. What is that in? 46.88 kilojoules per mole. Okay, that's EA, right? Relatively, it's not huge, right? We've seen kilojoules like 200, 300 kilojoules per mole for like our delta H's. That's not a huge activation energy. Knowing that it's not a huge activation energy, what can that tell you about the rate of this reaction? Pretty fast, right? Because we don't have much of an energy barrier to achieve, so it's going to be pretty attainable. So the activation energy is this. That means likely a fast reaction. Does it give us anything about the thermochemistry? Delta H, delta G, delta S? No, nothing, right? We could figure out if we had more information, but not from this information here. Okay, so that's how we figure out the activation energy. Let's do another one. This is in your packet. This next, I think the next one's in your packet. Yes, this is in your packet. So from the, did I move away too fast? Is that okay? Go back there for just 1 second. Pull out your packet to page, I'm going to guess and say 15. I could be lying to you. My packet is up here. No, not the packet from last night. This is actually in your packet, which has more questions which we'll get you shortly. So, we have about an hour. Oh, we have to do an earthquake drill. We'll take a moment to stop, drop, shake, and roll, and then go. No, not yet. Just let's do this first. So go to page 19. My bad. 19 for the main. The little circle number. Look on with somebody if you don't have it in front of you. These are more elaborate. These have more than one question. So I'm going to walk through the first example with you and then leave you with the second one. Give me a thumbs up if you found this. Thumbs up that you found this. All right, go ahead and input data. You already know that's probably the first step. Input your data. And then we'll talk about the questions.
Yeah, because on the website it said answer the questions too, so I did everything except for number 5, or like the very end.
I want to go over this. Hopefully you really want to give me some
The only thing I couldn't do was this one, because I clicked on the graph, I couldn't find the intersection. Like it is so like
Mm-hmm. But you can plug in. You can just take that value and plug it in. You know what I'm saying?
Kind of.
So like plug it into your y equals minus 50.
Okay.
Okay.
Gotcha.
All right, so I know you're putting data in, but at this point you should be seeing the values of k. Look at those values of k. Give me some descriptors. Really big. I was going to say enormous. Right? That's like a billion. All right, so very large value of k. Alvin, reaction fast or slow? Alvin, are you listening? Okay. So what did I just say about the value of k? Very large, right? Very large k, meaning rate law constant, means large rate, means fast rate, right? So it's fast, and then you're going to say that's because the k is enormous. Are you still enormous? Yes. The k values are very, very, very large. And as you're inputting data, you're seeing that the values are very large. Yeah.
What do you distinguish as an average K, but not large, not small?
So the Goldilocks k is like, let's say, gosh, that's a good question, Levi, because it's really hard to say because there's not really, there's no standard for that. I would say like 10. Like 10 per k is like, I'm kind of fast, but like I'm not too fast that I'm so fast you don't see the reaction happen. But like less than 10 and 1 and so forth, like that, like our rate law from yesterday, it's a rate you can actually see happen. Like we could see the crystal violet change color, right? You went from dark purple to clear. So this would be so fast we wouldn't even see it. Like we would probably have no idea that this even existed. This is like air pollution, right? Nitrogen monoxide. Who took AP environmental science? Levi and this whole table. Look, okay. So that's like some sort of from a scrubber, right? From a smokestack. I'm impressing you with my environmental. Okay, so that's ozone, reacts, makes oxygen, which is great, but we don't necessarily want that to happen. We need the ozone to protect from the UV sun rays. Okay, so overall order of this reaction. Jacob, tell me what you think, man.
The overall order of the reaction I said was second order.
Why?
Because the rate determining stuff is the NO and the O3.
Where do you see the rate determining stuff?
At the very other no.
There is no.
Okay, but
So you say second order. Can you guys tell me from the data given, how would you think you would even be able to attempt that? There's no mechanism, so we can't see that. I think you assumed that was the elementary stuff. That's just the overall reaction, which we can't pull data from.
gotcha.
You look at the units of K.
Look at the units of K. So what are the units of K? Say again? Per mole second? Or molar second, right? So liters per mole is molars in the denominator, right? Okay, so if that's in the denominator, what is the order? You were right.
It would be second.
It would be second. Why would it be second?
Because I kind of know how to explain it.
It's hard to explain. You're right. Go for it, AJ.
So for the units of rate is molarity over seconds.
Rate is molarity over second. Yeah. Molarity squared.
So it depends about using molarity on the bottom.
Right. Because you just need to make the units cancel out, right? So if you have something here and you have molarity squared here, one of the molarities has to stay on top, one of them has to cancel, and then how the heck does seconds just appear? It doesn't, right? You have to have it down here as well. And so that agrees here, definitely second order. You guys pick that up now from the data? Yes?
Yes.
Thank you. Okay, let's finish this one up. So you've had time to input your data. You've had time to learn reg. Can I get a raise of hand who can actually tell me the y equals mx plus b? Go for it, Jack.
Let's see.
1635.72.
Okay. The y-intercept.
Y-intercept is 28.0.
Okay, so there's our ln reg. From this, you can find your slope. And then, let me get somebody new. Avery, Arushi, Savannah. The girls are quiet today. How would I get to activation energy? Go for it.
You multiply by.
Okay, so that times negative 8.314 joules per mole K. And what do you get? I'm going to do one more after this, and then I'm going to set you guys free to do some on your own. Got me, Levi? All right, Rushi's got you, yeah. 11.9 kilojoules per mole. Oh, is that joules or kilojoules? Did you convert to kilojoules? Oh, okay, cool. So she took her joules. It was, I guess, 11,000 joules, and then she converted to kilojoules. Just making sure we're not, like, randomly saying kilojoules, right, Rushi? Okay. So she may or may not have done that on her test. We're joking. So this is our EA. What would you say about the rate of our reaction? Sean, what would you say about the rate of our reaction?
It's bad.
Why?
The
EA is low. EA is low. Rate is fast. What was the other indicator that this rate is fast? K values. K values what? Enormous. Thank you. K value is enormous. So that doubly makes sense, right? That's always nice when your answers agree with each other. Okay, so if I were, I may not do this right now, but if I were to solve for the K value at the temperature of 455 Kelvin, what would you guys do for that? What would you have to do? Savannah, what would you have to do?
Would you plug it into your equation?
Yeah, just plug that data in, right? So you have your equation already. You say y is equal to negative 1435.72. X would be what? 1 over, right? 1 over 455 Kelvin. And then our y-intercept is 28.07. When you solve for y, what does that truly equal? ln of k, not k, right? Please don't say that's the answer. It's not. So once you solve for y, that's going to be ln of k. How would you oppose? What's the opposite of ln? E. So e to the ln, e to whatever this number is, that would be your final answer. Yeah? Do you remember this math? How long ago was this math? You said a while ago, that gives me no number. How long ago was this math? Are you in this math? Was it last semester? Was it last year? Sophomore year? Oh, hold on. I have an answer for you on the wrong sheet. What are these sheets, guys? Does anybody have an answer?
Yeah, it's like 339.
Whoa. I got like 6.60 times 10 to the 10th. Okay, thank you. So very large number. What is the unit again? Units.
Per molar.
Per molar second. Good. Okay, so this is K. And does that agree with all of our other Ks? Yes, because it is enormous. Thank you. All right. I'm leaving that there for you. Here's my game plan for the rest. Who's gotten more than 20 questions on multiple choice? More than 20. Okay, so
That's what I forgot.
it's okay. I'll do you guys a favor. Let's do multiple choice first. Then we'll jump into free response. I'm assigning you guys the presentations for free response because I feel like when I talk to you, you just sketch the world. Maybe it's that second period syndrome of I've already gone through first period, I'm overwhelmed. But you guys are presenting these tomorrow and Friday. I'll tell you when, like specifically who's doing what. But start on the multiple choice right now. Work as a group if you want to. Get up and move. Then we'll do our earth breaks and stuff in a second. You guys have 45 minutes. Let's knock this out. Multiple choice. Multiple choice. Yeah, you're going to do free response, but I'll show you where it is in your packet.
Yeah, I figured out last night. Because I was first finding out when this was. I didn't realize it's
See if you can do that.
You can find your free response in your packet. This is the first one. But I'd go ahead and work on multiple choice first.
Yeah, I forgot my second home.
So if that means you can just like save it if all on the same side.
Last week, and this one gets all the blurs. You know what's happening? This is my result so far.
Yeah,
For our project, not real life for our project.
I was just like,
That's really
I'm gonna in the background play the announcements right now. Because there's an earthquake drill, a public service announcement. We're gonna do that. We'll practice it in just a second. Miss Whitley, not pregnant. It's so jumpy.
Jimmy does what he's supposed to do. He is properly getting under the neck and covers his head. Good job, Jimmy. Observe what happens when Jimmy does not practice different safety procedures. See how debris falls on Jimmy's head? Do you want debris to fall on your head? No, you don't. If you happen to be in the hallway when an earthquake strikes, and you are not near a table or desk, then drop to the ground in the inside corner of the building and cover your head and neck with your hands in your arms. Sally is doing just that. Good job, Sally. To ensure your safety, please be sure to follow the steps that Jimmy and Sally have shown you. This tour is brought to you by Broadcasting 3. Stay safe, Chargers.
I pledge allegiance to the
We're
flag.
gonna skip the pledge a minute. This is what you need to see.
Let's find out what's for lunch. See you tomorrow. Hey, Charger, I'm Grace. And this is your Charger Sports News. There will be a men's volleyball meeting tomorrow at 2:20 in Coach Keith's classroom. There will be a JV and varsity basketball meeting for boys and girls on Friday. And congratulations to the men and women's swim team for winning against South and West Berlin last night. Go Chargers! Pointing girl. Hello, Alice. Frank.